Welcome to Mechanical Engineering webinar, Waterhammer Transients and Pipe Forces, what they are, and how to simulate and analyze your system to mitigate damage. I'm Alan Brown, Senior Editor of ASME's Mechanical Engineering magazine and today's moderator. Today, we are going to learn about Waterhammer forces, how to analyze them, and how you can use that knowledge to prevent Waterhammer damage. Our sponsor is Applied Flow Technology, a leading provider of fluid dynamic simulation software that gives engineers insights into what goes on in their pipes and pressure vessels. Before introducing our speakers, I'd like to say a few words on our topic. You probably already know what water hammers are, sudden transient spikes in water pressure. When they occur in a piping system, all sorts of bad things happen. If you want to see what I mean, try Googling Waterhammer Damage sometime. It brings up great pictures of ruptured pipes, exploded valves, warped expansion joints, and broken heat exchangers. This type of damage is costly to fix, especially if you count lost production if you're running the factory, and sometimes dangerous to be around. Today's seminar will focus on how you can use software to analyze piping and pressure vessels and design solutions to fix those issues. With us today, to fill you in on the details, are ATF President Trey Walters and ATF Technical Consultant Ben Keiser. You've already read the bios, so I'll be brief. Trey founded Applied Flow Technology in 1993 and was the original developer of the company's fluid dynamics simulation, compressible flow simulation, and Waterhammer and surge analysis software. Trey was recently elected an ASME Fellow for creating and advancing commercial fluid system engineering simulation tools. Ben has a strong background in chemical engineering and is one of ATF's experts on pipe flow analysis. He has helped engineers around the world develop piping and ducting systems and has a strong background in water hammer and surge issues. Now, before I hand off the webinar to Ben and Trey, I want to mention a few simple housekeeping rules. First, the console you're looking at is completely customizable. You can move, enlarge, or collapse every window. So go right ahead. Second, this is an interactive webinar. I'm sure you're going to have questions. So please click the Q&A widget on the bottom of your screen and ask them while they're still fresh in your mind. We've set aside time at the end of the webinar to answer those questions. And if we don't get to your question, Trey and Ben will respond to as many unanswered questions as possible by email. Now, there's a way to get more information on this topic and a copy of the slide deck. Click the resource widget at the bottom of the screen. That's the document icon at the bottom of the screen page. If you need to leave work early, don't worry. We'll send you a link for on-demand viewing tomorrow. Feel free to share it with your colleagues. So let's begin. Trey, Ben, take it away.
Thanks, Alan. This is Trey Walters. I'll be beginning the presentation today, and then we'll pass it over to Ben a few slides down the road. A little bit about Applied Flow Technology. We are in our 25th year in business as a provider of pipe flow simulation software. We have customers in 80 countries, and we have engineers all around the world using our software every day on projects related to oil, water, chemicals, cryogens, aerospace, all kinds of things like that, steam, things like that. So today we're going to focus on Waterhammer. And on the first topic here on our agenda, I'm going to talk a little bit about some of the codes and standards that are out there, some accidents, and then Ben's going to talk a little about some equations and physics, et cetera. So let's go ahead and dive in. Codes and standards for Waterhammer. Unfortunately, there's little guidance that exists out in organizations providing guidance on Waterhammer from a code and standard point of view. Engineers are expected to use judgment and experience. There is a little bit that you'll find, for example, in ASME B31.4. And it talks in here, I'm not going to read this paragraph, but it talks in here where it really starts off is surge calculation shall be made. And surge is another word for Waterhammer. We'll talk about that in a moment in the English language. And that says shall be made, which if you're endeavoring to comply with 31.4, you're obligated to do some sort of calculations for Waterhammer. And there's some guidance in here on what levels of Waterhammer are allowable. Over in ASME B31.3, there's also some guidance in here, and it talks about allowable pressure that you can experience and some things related to safety factors and allowable stresses in here. And so again, I'm not going to read this, but there is some language in the standard there. What I also will mention is that there is a Waterhammer guideline in development called ASME B31D, and that is being worked on, and as I understand, being discussed this week in Baltimore, Maryland at a ASME B31.3, one of their meetings that they have this year. So that might be something that's coming out soon and provide some additional guidance. As far as terminology, Waterhammer can occur in any liquid piping system, and the term is a little bit confusing in the English language because obviously the term water is part of Waterhammer, but Waterhammer used more generically is really in any liquid system. So you can have Waterhammer in an oil pipeline, you can have Waterhammer in a liquid oxygen line, etc. So it's such a general term that certainly originated related to water, but now is applied in general to liquid systems. So there are some other terms in the English language that you will see used on occasion. Certainly, I think the second most popular term is the final one here, surge, and that's a synonymous term. It means the same thing. The second term here, hydraulic transient, is another very popular term. You'll hear fluid hammer, you'll hear fluid transient, and they all mean the same thing. I'm going to go and show a video here, and there's a YouTube link, and you're welcome to click that after and go watch this, as it is out on YouTube, and it shows you a little bit what happens when a valve closes in this system. This is something that was a video taken back in the year 2000, and so from there, we'll go let the video go, and I'll conclude after the video plays. As Alan alluded to earlier, there are a number of Waterhammer accidents that you can find Waterhammer damage by just going out and Googling. I'm going to just share two with you. One is an accident that happened in the year 2008, about an hour from our office in Colorado. This is in Denver along Interstate 25. What you can see over on the right is a major highway that goes through the city of Denver, and the damage that happened when a 66-inch pipeline burst after a pump failure. And you can see the pipe on the left there with the man standing on it that was damaged during this accident. Another accident that happened a little further away from us here in Colorado, and this was in Europe. This was the second biggest oil spill in Norway's history that happened in the year 2007. There, you can see in the center there's a map of where the Stratford offshore facility existed. And there was a transfer from the Stratford A platform over on the right to the ship on the left, and there was a 20-inch hose that burst after a valve slammed, and it caused over on the right an oil spill of over 27,000 barrels of crude into the ocean there. And there actually was a paper written on this for the Society of Petroleum Engineers. There's a link down below. So these things are things that you can find when you go out and you search on the internet. So if we continue forward here, that's a very common concept in Waterhammer, understanding Waterhammer, is the concept of instantaneous Waterhammer. So we're going to start with this with a part of that called the liquid wave speed. And the wave speed, commonly used as symbol A, and some people will call that C. It is based on the liquid acoustic velocity, first and foremost, which itself depends on the density of the liquid and the liquid's bulk modulus of elasticity. It also depends on the pipe material and the modulus of elasticity of the pipe, Young's modulus, the wall thickness, and the Poisson ratio, and to some degree how the pipe is restrained and whether it's buried on hangers, how rigid it's restrained. All of those influence the propagation wave of the wave speed A. Typically, what you'll see in English American units is 3,000 to 4,000 feet per second. In metric units, maybe 1,000 to 1,300 meters per second would be a very common wave speed that you would see. So there's a maximum theoretical pressure surge that's given by a very famous equation attributed to Joukowsky, a mathematician in the late 1800s and early 1900s. In pressure form, it looks like this. The delta P pressure spike is equal to the density of the liquid rho, the wave speed A that we just talked about on the previous slide, and the instant change in velocity. So an example here is density of essentially water, a wave speed of 3,000 feet per second, about 915 meters per second. The initial velocity of the liquid that's being stopped 10 feet per second or 3 meters per second. And just the operating pressure at the valve, 100 psi or 7 bars. So you can put these numbers into the Joukowsky equation, and what you'll see is that the pressure spike that results here, the rho A delta V, is 400 psi or 28 bars, okay? And that brings the total pressure maximum to 500 psi or 35 bars. That's just an application of Joukowsky's equation. Something to caution engineers on, and certainly when I first learned the Joukowsky equation many years ago, it was taught to me as being, as the top bullet alludes, it's the maximum theoretical pressure surge. And if you use this equation, you're always have a conservative answer, and you cannot exceed this. This is actually not true, and so you should be careful with this. As the final bullet here points out, there's a paper that was written just last year for an ASME conference. I was a co-author. And it talks about cases where you can get higher pressures than this, what we're showing here in this example, under certain conditions. So be careful with that, and if you're interested, go Google the Walters and Lashire paper from 2018. It was an ASME PVP conference last year. Another key concept in understanding Waterhammer is communication time. This is the time it takes for transient events to communicate their existence back to the point of origin. It's given by this equation right here, delta T equals 2 times L, which is the length of the pipe, divided by the wave speed A. If you have an event that occurs in a time frame less than this delta T, it's in effect instantaneous. And so there's some examples here in this table down below, some with a wave speed of 4,000 feet per second or about 1,200 meters a second. You have different pipe lengths in here, and on the right is the communication time. So if you have any event with a pipe length as shown in here in this table, less than over on the right, 0.1 seconds, 1, 10, or 100 seconds, given the certain length of the pipe, you're going to get at least the Joukowsky pressure spike you're going to experience, even if it doesn't happen instantly. So, for example, the third one here has a communication time in a 20,000-foot pipe, 6,100-meter length pipe, 10 seconds communication time. So if you have a valve that you close in 9.5 seconds, you're going to get the full Joukowsky pressure spike in a situation like that. This chart here is going to show us just the Waterhammer sequence and kind of the physics of what happens when you have an instant valve closure. We're going to start with the top left here. We'll call that phase A. This is a time frame of where the time is greater than 0, but it's less than the L over A in the system. What you can see here in this chart is on the left, there's a reservoir. At the top left, there's a reservoir. And at the right, there's a valve that's closed instantly. And in the middle there, there's a dashed line. That's the location of the wave. It's propagating to the left at a velocity A, which is something like 1,000 meters per second, maybe 3,000 feet per second, pretty fast. To the right of this wave, the velocity has been brought to stop because the valve is closed. But to the left of this wave, there hasn't been communication yet to the liquid in this part of the pipe. So even with the valve closed at this instant in time, there is still fluid coming in from the reservoir on the left, coming into the pipe at the original steady state velocity. If you look a little further down where it shows the graph of P steady, and there's a purple graph, you'll see the pressure in the line, and then there's a spike right there at where the wave location is, and that's the Joukowsky pressure rise right there. And then below you can see what the profile is over this distance of the velocity. And you'll see where the wave is. To the right, the velocity is 0, but to the left, the velocity is still at the original steady state level. If we go over to phase B, what's happened at this point in time is we're at a time that's greater than L over A in phase B, but less than 2L over A. The wave has reached the reservoir. Now it's reflected, and it's traveling back from left to right, and you can see the location there in the center on the dashed line. In this situation right now, the pipe is under high pressure, and so it goes through a process of trying to reduce that pressure. So the velocity actually reduces, and we get backflow from the pipe going backwards back into the original reservoir as the wave propagates from left to right. And you can see that in the lowest graph down here, the velocity graph on the profile, that you can see that the velocity is negative now, and it's equal to the negative of what was originally the steady state velocity. It's now that value, but in negative. Once the wave reaches the valve, as it's traveling left to right, then now we've established communication between the valve and the reservoir so they can cooperate to bringing this whole system into equilibrium. We're going to progress now into phase C, down in the lower left. The time is greater than L over A, less than 3L over A, and now the wave is traveling again from right to left. Okay, it's very similar to phase A, but what you'll see in the pressure profile there in the center, the graph with the purple graph, the pressure now is dropped at that wavefront, and it's the negative of the Joukowsky pressure rise. So in phase A, there's a pressure increase equal to Joukowsky. In this case right now, after this reflection happens, the pressure is now reduced by the magnitude of the Joukowsky pressure rise. This can cause problems in a lot of systems because if that pressure reaches the vapor pressure of your liquid, you can start causing cavitation and flashing of your liquid, which can cause all kinds of problems in operation and other secondary pressure spikes that are even larger. So that's something that you would really be advised to avoid. Once the wave now travels all the way to the reservoir for the second time, we're going to progress over to phase D in the lower right. Now the wave is progressing from left to right again. It's going back towards the valve, and as it does so, it's bringing the pressure and the velocity back to the original value. And if there's no friction in the system, this will repeat forever as basically a square wave that just goes on forever without any damping. In reality, the friction in the system, the elasticity of the pipe will have a decaying square wave over time. So we're going to progress right now over here, and I'm going to show you a quick video of what's going on here in a system that is a pipe system that is 20 feet long. We'll call that about 7 meters. And there's a valve on the right that's closing instantly, and we're going to watch the wave propagate. So on the top graph, that's the pressure, and on the scale on the left, it's in PSI. The scale on the right, there's another y-axis, that's in bars. And then on the bottom is the velocity. And so the velocity, you'll see in the center, there's 0, and it goes down to, on feet per second, -8, and in meters, it's -2. So you'll see the velocity go negative when I start this graph. So I'm going to go ahead and start this, and you can watch when the wave begins. And we're not starting here on this video. Oh, here we go. And you can see the wave going back and forth, and now we've got the pressure at the top has gone to a negative pressure from initial steady state pressure, and the velocity is negative. Now it's reflecting again. And when the wave reaches across to the right at about, 18 milliseconds, then it's going to reflect and repeat over again. So we're going to stop this right now and go on to the next chart here. And my colleague Ben here at AFT, he's going to show you an example how you can simulate what I just showed you in the video with simulation software with our AFT Impulse. So Ben?
Thank you very much, Trey. And I'm going to demonstrate an example here of a simple valve closure similar to the one that Trey was demonstrating with the Waterhammer Sequence process. And this particular example of a valve closure comes from Wiley and Streeter. And it's going to be demonstrated with a software simulation tool called AFT Impulse. So the system that we're modeling here is going to be a simple water system. That way we can get the thermophysical properties of the fluid. So it's water at 18.3 degrees Celsius. The supply liquid reservoir is going to have a liquid surface elevation of 150 meters, and the pipe is going to be connected at the bottom of the reservoir, and that sets up the supply pressure. And the pipe itself is going to be half a meter in diameter, 600 meters long. We're specifying a wave speed of 1,200 meters per second with a known friction factor, and we are discharging through the valve into the atmospheric conditions. What we want to look at is to compare the results for a linear closure versus a nonlinear closure. And this example right here is of a nonlinear valve closure that will be seen here shortly. Before I go into the example, though, I want to jump to the next slide really quick just to go through the fundamental equations that are being solved. So in order to capture the water hammer in the system, we're going to solve the transient mass and momentum balance equations, and there are two common methods that are able to solve these equations here, the method of characteristics and the wave method. And Impulse is going to use the method of characteristics. Now, in terms of solving these equations, I'm going to show my screen now here. It is certainly possible where you could easily build your own spreadsheet to do the calculations yourself. And this is a spreadsheet that I have of a simple valve closure example, and I'm scrolling over to the right, and the results go all the way over to column CC. And this generates a graph of how the pressure changes at the valve over time. So to simply calculate how the pressure at the valve changes over time, we need several columns and rows of data. And imagine trying to apply this to a more complicated system. There are several areas where things can easily go wrong with entering a typo into the equation. So a major advantage to using a software simulation tool like AFT Impulse is that you don't have to program any of the calculations or equations into the program yourself. And that way, instead of having to double check all of the typed in equations for a checker that's checking your work, they can simply double check the input itself, and it makes it a lot easier and can really reduce the amount of error in the model itself. One thing I want to point out is that AFT Impulse has been fully verified and validated for usage in safety-related systems in the nuclear industry, and this is the interface for what AFT Impulse looks like. So where do you start from here when you want to build a model of a valve closure example? Well, the best thing to do is to follow the yellow brick road, which is the little red status light in the bottom corner of the interface. This will allow you to go through and figure out what steps you need to complete so that you can do your Waterhammer analysis. The first item is already completed. The next thing that needs to be done is to specify the system properties. That's simply the fluid information. So as I walk through each of these steps one by one, I can complete the process to be able to get results. Now, the next part of the yellow brick road is blue highlighting that's built into the software. I can toggle the blue highlighting on and off with the F2 button on my keyboard. So really the minimal information you need is density, viscosity, and bulk modulus, but there are ways to simplify this even further. So if I go to specify water, which is the fluid I want to work with, I can add that to the model, and as you can see, the only input that is required now is simply the temperature. So that reduces the amount of input that I have to specify. So our temperature here is 18.3 degrees Celsius, and when I calculate that properties, they're all done for me, and I've got my second green check mark. The next step is to define all pipes and junctions. So this is where you would use a mixture of the components on the left-hand side here to build a model of the piping network of your system. So I'm going to use a reservoir to model the supply reservoir in the example, a valve, and a pipe. So it's a very simple drag and drop interface. And in order to define your system, you can click on this button right here, and this will tell you exactly what you need to specify. The red highlighting that you see for each of these labels indicates that it's missing some input for the model. The next thing is if you click on any of these items in the left or in the right-hand panel, it tells you exactly which pieces of information are missing. So it guides you through every step of the process so that you can easily model your system. So I'm going to just start double-clicking on stuff to define their input. So if I double-click on the reservoir, here's my blue highlighting again for required inputs. And if I turn that off so it's easier for you to see, my liquid surface elevation is 150 meters. And then my pipe elevation is going to be at the bottom of the reservoir at 0. Now that I've fully defined it, you can see how the label has turned black. That means it's fully defined. And then I just go on to the next one. I'm going to define my pipe. Again, the blue highlighting indicates the required input. There's a lot of parameters that you have to specify. But if I specify the wave speed directly, you can see how it simplifies the amount of input that I need for the calculations to take place. I'm going to turn that off so you can see the input a little bit better. So my inner diameter is 0.5 meter. The pipe is 600 meters long, and my wave speed is 1,200 meters per second, and the known friction factor is 0.018. And now my pipe is fully specified. The last thing I need to do is the valve. So if I double click on the valve, the elevation has to be specified. That's just going to be 0. Now, the fully open CV value for this valve is going to be 529.9. And it's discharging right out into the ambient conditions. So I'm going to specify my atmospheric pressure that the fluid is going to be discharging into. The last part is to define the transient. The transient is what's going to dictate how this valve is going to change over time, and this is what's going to cause Waterhammer. Now, to compare and contrast, I'm going to do 2 separate profiles. I'm going to start by using a simple linear valve closure where it closes linearly in 2 seconds. And so what I'm going to do here is I'm going to select this data and copy it, and then go back into Impulse and just paste it right in. So when I show my graph, you can see how this is going to be the linear closure. And just so that I know it's a linear closure, I'm going to put that in the name, linear closure valve. And there it is. So now I've got my system built, but what I'm going to do is I'm going to select the system here, and I'm going to duplicate it, which is basically a copy and paste in one. And that way, all I need to do is open up the second valve. I'm going to change the name to call it nonlinear closure. And then on the transient tab, where I define how this valve is going to change during the transient, I'm going to clear out that data, go back to my spreadsheet and copy the information. And then I can go back into Impulse and then just paste it right in. And then you can now see that it has a very slight dip in the profile and how this valve is going to close. And you'll see that this certainly can make an impact on the maximum pressures that are going to be seen in the system when that valve is fully closed. All right. Now, the last two steps that I need to do is to section the pipes and specify my transient control. I'm not going to spend too much time on what these are. Essentially, I am breaking the pipe up into bits, and I'm going to specify computation stations along the 600-meter long pipe at every 20 meters. This way, the method of characteristics can solve the transient maximum momentum balance equations. My time step here, if you notice, is 17 milliseconds. Last thing is to specify my transient control. This is simply how long I'm going to run my simulation for. So my valves are closing within 2 seconds, but I want to see what's going to happen 10 seconds after that as well. So that's my full simulation period, and then I'm going to save the results for all the interior computation stations every 20 meters along the pipe. That way I can graph everything I need to. And now you can see that in less than 5 minutes, I have all green check marks and a green status light, and I'm ready to run my model and generate results. If you want to have a race with me later on, you can see how long it would take you to build this spreadsheet versus how long it would take you to build the model in Impulse. All right, so when I go to run, it's going to have me save. So I'll just call this valve closure. And it runs really quickly here. And so there are different ways that you can examine your your output results to capture the Waterhammer in your system. And the first thing you might look at is the output window. This is just a summary table that essentially tells you what the maximum and minimum values are that you'll be seeing for pressures, flow rates, velocities, etc. But the best way to analyze your results is to create graphs. That way you can see exactly what's going on. So if I go back to the workspace, what I want to look at is how is the pressure changing at the valve when those two valves close. So if I select these two valves on the workspace, I can right click and I can generate a graph of the pressure. Now I'm going to tidy this up a little bit. As you can see, I'm only showing the pressure results in terms of PSIA. So what I'm going to do is I'm going to create a secondary y-axis. That way it shows you the results both in PSIA and in bars. So this is comparing the this is comparing the transient pressures at the valves, and if you look at the maximum values for both of them, we can see here that for the linear closure case, our maximum pressure is 386 psi. If we were to look at the maximum pressure for the nonlinear case, that's going to be 397 psa. So when you compare this to the original steady state pressure, which is 218 psia, what you would see is that the total pressure surge when that valve closes first is about 170 to 180 psi. But here's the advantage for a nonlinear closure is that it dampens out a lot faster than the linear closure. So this is just a good example to demonstrate how the way you close the valve is just as important, if not more important, than how long you're taking to close the valve. So that's the example in AFT Impulse. I'm going to go ahead and jump back into the slides here. And so now we've seen the equations. There are some important questions that can be answered by doing a Waterhammer analysis. And one of them is simply to help you predict maximum pressures in your system. This is to help you avoid bursting the pipes. So you'd want to compare your maximum pressures with the pressure ratings in the pipes, and that way you can ensure that they're lower so you avoid pipe bursting. Low pressures are just as important, because if you have low pressures that are causing vacuum conditions inside the pipes, that can potentially cause your pipes to collapse, and that would be a problem as well. So those are some questions. It also helps you understand the MPSH for your pumps to make sure that your pumps are not cavitating. It can help you predict transient forces. So when your pressures are changing throughout your system, your forces are going to be causing loads on the supports as well as your equipment. And you want to make sure that your supports are strengthened appropriately and that the transient forces are not tearing up the valves and other pieces of equipment as well. And then cavitation could be a major issue. If you have cavitation happening, that's where your system pressure reaches vapor pressure. And when those vapor volumes collapse, it's like popping balloons inside of your pipes, and that can cause very high pressures. And so the moral of the story is high pressures and lower pressures are critical to avoiding your system. And then this can also help you size and locate surge suppression devices like vacuum breaker valves, relief valves, different things like that. All right, I'm going to go through the next few slides here fairly quickly, because this is just to provide a little bit of background information on other pieces of equipment that can influence Waterhammer. Pumps can cause Waterhammer in your system, such as pump trips or pump starts. Basically, anything that causes a change from steady state behavior is going to send pressure waves passing throughout your system. And then if you have check valves downstream of your pumps, that also will cause a different type of response in your system than if you did not have check valves. And so it's really key to make sure that you're modeling your pumps appropriately for doing pump trip analysis or pump starts, in addition to just a simple valve closure. Now, if you do not have check valves in your system, it is possible that you can have reverse flow. I'm just jumping forward to that slide here. If you have reverse flow through your pump, or if there's potential for your pump impeller to spin backwards, then your standard pump curve that you're getting from your manufacturer is not going to be able to accurately predict the pump head when you are in those circumstances. This is what's called a 4-quadrant data set, and that can help you predict the pump behavior when your pump is either spinning backwards or has reverse flow. It can be difficult to get that information from a manufacturer, but there are various published known 4-quadrant data sets, and what you would do is you would match up the 4-quadrant data set that is published and references for a certain specific speed, and you can try matching that to the specific speed of your pump, and that can give you a potentially reasonable approximation for how your pump is going to operate in those circumstances. And there are different ways to be able to do that. And there is some important research, though, that needs to be taken into account when you're trying to match up those curves, and that's something that we can look into further. All right, as I mentioned before with valves, not only is how fast you close the valve important, but it's also how you close the valve. And different types of valves have different types of characteristics for their open percent versus CV data. And this will impact the pressure surge that you would see in your system. And this can help you determine if you have the right valve for the proper application. So that's important to consider for Waterhammer analysis as well. Check valves also influence Waterhammer in your piping system. There are several different types of check valves, but common types are swing check valves or nozzle check valves. In a nutshell, you don't want to just throw a check valve into operation and hope that it works. When you do a proper Waterhammer analysis, you can make sure that your check valve is actually going to help mitigate the surges in your piping system, because if they start to chatter or when they slam shut, that can cause significant pressure surges in your piping system. Just a couple more things. I'm going to skip this video that talks about transient cavitation. You can watch it on your own, but this is a really good demonstration of how high your pressures can actually get if you have cavitation in. So if you watch that video, it'll go into good detail on that. And I'm going to stop that video and go to the next slide.
The Waterhammer effect. What is really happening during Waterhammer effect?
There we go.
Sorry about that, everyone. I was trying to move past the video. But just long story short, transient cavitation is when your system pressure drops below your vapor pressure and a vapor volume can form. Like I said, it's similar to popping balloons inside of your pipes, and that can cause very high pressures and cause a lot of damage. It is difficult to predict transient cavitation because in reality, your wave speed is changing, but with various cavitation models, they're not going to always capture how your wave speed is actually changing. So this is where the models can start to differ from reality. And there are two popular models for evaluating cavitating behavior: discrete vapor cavity model, discrete gas cavity model. Impulse has both. The discrete gas cavity model is better because it tends to smooth out the pressure surges and spikes that you would see by having a ability to closely mimic how the wave speed changes when you are cavitating. So this is just another important thing to analyze when you're doing a Waterhammer analysis. All right. As far as surge suppression goes, there are lots of different ways to be able to minimize your surge pressures that you're seeing, either changing the pipe materials or decreasing your initial pipe velocity. And so this is one way to help mitigate surges that you would see. Another way is to change the way your components behave. So allowing your valves to close over longer periods of time or changing their profiles. As far as pump transients goes, adding flywheels to help the inertia on your pumps. Those are all different ways to help mitigate Waterhammer. And then there's also several types of surge vessels that you can incorporate: relief valves, gas accumulators, surge tanks, etc. Okay, Trey, back over to you for going over pipe forces.
Thanks, Ben. In the next couple minutes, let me go ahead and conclude with pipe forces and some references to a couple case studies, and then we'll turn it back to Alan for some question and answers. Let me see. Where are we? Pipe forces. Here we go. So what happens when a Waterhammer wave goes around an elbow, and especially around elbow pairs, it causes a temporary imbalance of forces, and this can be calculated using Newton's laws with a force balance. And this is one of the things that comes out of a Waterhammer software like AFT Impulse. And you can use this, for example, in a situation like we're showing in the pipe system on the right, along a couple elbow pairs here, about 500 feet long, 150 meters. And you have some forces which are generated in the graph here. And you can do one of two things. You can pick out the maximum force, and you can use that as part of your pipe structural design. And you can also get the time varying force, and you can put that into different pipe stress software to see how it interacts from a time history point of view. Impulse does export forces into really into any commercial software, most easily into software such as Keiser 2, Triflex, and Roar 2. And there's a paper with a link down here at the bottom that describes kind of how to do that. I want to just make reference to a couple case studies really quickly before we conclude. I'm not going to go through all of these just for time limitations, but I'll tell you this first case study here is the municipal water pump station in Barcelona, Spain. It's a pipeline that's 0.8 miles long, 1.3 kilometers, elevation rise 450 feet, 137 meters. The pipe is a 12-inch, 30-millimeter pipe. And this was documented actually in a technical paper last year in 2018 in Bordeaux, France. You can download that on the internet, and also you can read some of this on the slide deck here. There were check valves in the pump station here that you can see on the blue axial pumps you can see on the left, and then one of the pumps had a swing check valve, one had a nozzle check valve. There's a simulation model built with Impulse that looks like we're showing right here. And this is described in this technical paper. And then there were some measurements taken on the swing check valve. On the graph at the top is the blue was measured, and then the gray was what was calculated by AFT Impulse. And the nozzle check valve on the bottom is the orange, and predicted by Impulse. So the conclusions from this is that you can use simulation software to simulate this. The nozzle check valves have a lower pressure surge that result after a valve slam. Another case study that was presented at the same conference in Bordeaux, surge mitigation in a marine fuel oil terminal. This shows a marine fuel oil terminal in the United States Gulf Coast area. And altogether, there was there were hundreds of combinations of operating cases modeled. Well, this particular case study focuses on one. But in all of the simulation, there was 40 miles or 65 kilometers of network piping. This is a very simplified one on slide 44 of one of the ones that was modeled. It was a 2.3-mile long pipe going with 3,700 meters, going from a tank out to a ship dock on the right. And then there was a gate valve that is shown right here in red that was closed over a time period of anywhere from 70 to 160 seconds. And then there was with and without a surge relief valve that's shown here in the model on the right. And then there were some different results that came from the different cases that were considered. And this is showing pressure versus time at this place where the gate valve is the red arrows pointing to. The lower left was the recommended situation for this particular facility, a nonlinear dual rate closure with a surge relief valve skid that was below the red line, which was the maximum allowable. And the conclusions in here were you have to be careful using when you introduce secondary flow paths like a relief system. That can actually cause secondary pressure surges, and you have to be careful to evaluate that. This particular case had a creative dual rate actuation, so they slowed the valve down on the actuation in order to reduce peak surge pressures. And with that, I'll turn it back over to Alan for any questions.
There are a lot of questions, but first, thank you, Trey and Ben, for a great presentation. It was really meaty, and I'm really sorry all our listeners couldn't get continuing education credits for this. But now let's get to some of the questions. So, give me 1 second here. There we go. Let's start with an easy one, which I think you just answered. Can pipes be modeled with varying elevation profiles?
Yeah, this is Trey, and that's an important thing to take into account if you want to be able to determine peak pressures on the high and the low side. So the answer is yes.
Okay. Can your software, AFT Impulse, model non-Newtonian fluid behavior, things like, say, pulp and paper systems?
Yes, different non-Newtonian fluid behavior, pulp and paper, things that go on in food products, chemical processes, and Impulse can model all that with non-Newtonian fluid models, including settling and non-settling particles in the fluid.
What about starting the model with specifying maximum and minimum operating pressures?
Yeah, Impulse can do that, and the user can specify any number of design levels, maximum, minimum, and those are incorporated in the software, and you can use those when you create a graph.
Excuse me for the background here. I'm in New York, and it's obvious there's something going on outside. So let me move right on. Here's another question. Can you calculate Waterhammer on a seawater injection well? I have a case where we collapsed tubing on a deviated well.
Yes, the Impulse can be used on injection systems like that. If we're still talking about a liquid system without appreciable vapor in it.
Okay, and does your software AFT Impulse take unsteady or frequency-dependent friction into account?
The current version does not. We're actually working on implementing a frequency-dependent model right now. We're in the process of doing that. So that's something that we anticipate including in a future version.
Okay. Let's see what else we have here. Can you handle elastic plastic pipe behavior?
Yeah, most simulation software, such as Impulse, is treating all of the liquid and pipe interaction as elastic. So there's no plastic behavior on the pipe. So an engineer would have to use judgment on any plastic deformation, but everything is elastic.
Okay. So there's an example. Can data from another pipe flow calculation software be exported and used by AFT Impulse? This person mentions, I can't tell if that says, but, well, go ahead. I can't quite understand the rest of it, so. But can you import it?
Yeah, I'm trying to see the entire question, but we import, Impulse imports data. It depends on other software and what they can export, but Impulse can take in data from various different formats, including EPANet. It can bring things in from GIS data. It can bring things in from Caesar 2 models. And it can also, Caesar 2 neutral files, and also piping component files, PCF files, which are supported by a lot of different CAD software. So it depends on what can be exported from the other software. But there are a lot of different formats that Impulse can bring in.
Okay. One other thing, this is Ben speaking, one other thing I want to add to that is if you have a AFT Fathom model for your steady state system, AFT Fathom models can be imported directly into AFT Impulse.
Okay, excellent. Can AFT Impulse model transients caused by positive displacement pumps?
Yes, Impulse can model both centrifugal and positive displacement pumps, something we didn't talk about today, but there's an add-on module, maybe for a different webinar sometime, that can actually evaluate the natural frequencies that are excited in your piping system from a PD pump, so that you can understand those acoustic frequencies to be careful to avoid those or design for those. And so the answer is yes on multiple levels on PD pumps.
That's a really sophisticated feature, isn't it? what about modeling transient cavitation?
Yeah, Ben talked about that in a slide. Ben, do you want to talk about that again?
Certainly. AFT Impulse contains two different cavitation models, the discrete vapor cavity model and the discrete gas cavity model, and those can be used to determine the volume of the vapors that can grow during a Waterhammer event. And the discrete gas cavity model I mentioned is a little bit better because it has the ability to mimic how the wave speed would change in reality, and that can help better reflect the reality of the pressure spikes that you would see upon vapor collapse. Trey, is there anything else that you'd want to mention in regards to cavitation?
No, you did it.
Good. This question goes over a little bit of something we've already had a question on, but it's different enough that it's worth asking. So does your software take into effect the effects of fluid structure interactions, say pipe inertia, pipe bending, pipe stiffness, on the pressure distribution and flow calculation?
Yeah, that is a great question, and I think the state of the art right now is, at least in the commercial world, is there's not really a good way to handle that fluid structure interaction. So the answer would be no, because there's not really a good accepted way of doing it right now.
Okay, good. And, this is a really interesting question. Can you simulate Waterhammer for a two-phase fluid case?
Yeah, that is a very complicated situation, and so AFT Impulse is not designed for that. I think there is software out there that tries to do that. It's quite expensive, but it does exist.
Okay, good. And here's an interesting question. How are pressure surges used to assist design of external pipe supports, assuming that maximum surges are kept below the minimum pipe wall stress levels?
Yeah, that was something that I alluded to in the slide that I'm showing right now, that what just kind of comes out of any Waterhammer simulation, if an Impulse does this, it captures the pressure, the transient pressure differences and the forces that occur between parts of the system, and that would affect your pipe supports. So engineers are able to take this information, and what you would see in the next slide here, some of the force versus time and the peak forces, and use that and evaluate typically in another pipe stress software and use that to determine the pipe supports. So that would be a typical process. At the bottom of this slide 36 that you're seeing right now, there's a white paper that talks about how to do this between Keiser 2 and AFT Impulse, and it takes with screenshots, it takes you through that whole process. So that would be something that would be a very common application for Impulse.
Good. Wow. That was a master class in asking questions. That was excellent. And great, succinct answers, which is not always the case. So I'm afraid, though, that we've run out of time. So let me thank our presenters, Trey Walters and Ben Keiser, and our sponsor, Applied Flow Technology, once again. For everybody still listening, remember, if you missed any part of this presentation or want to share it with colleagues, you will get an email that links you to this recording tomorrow. If you want more information about Waterhammer transients, just click the document icon at the bottom of your screen, where you can get a copy of the slide deck and also a bunch of interesting case studies. And finally, thank you all for joining us today and for all your terrific questions. Thank you very much. This is Alan Brown at ASME.org and Mechanical Engineering Magazine signing off.